Hello everyone. Today I want to talk about my work on preparing uniform quantum state using a Boolean approach. I will follow this outline. First, I want to define quantum state preparation problem. Next, I will introduce uniform quantum states. Next, I will present my proposed Boolean approach for uniform quantum state preparation. Next, I will present my work utilizing decision diagram for UQSP. Next, I will present my work utilizing functional dependencies in UQSP. In the end, I will conclude my work. A quantum state over n qubit is defined as this formula. We have superposition of all basis state, and each basis state is multiplied to an amplitude of alpha, and a squared amplitude shows the probability of being in the corresponding basis state. So one condition should be satisfied, that is the summation of all squared amplitude must be 1. Every quantum algorithm requires a special initial quantum state in the beginning. So quantum state preparation problem is an important task in quantum computing, while the quantum state preparation problem is in general an exponential problem. To avoid this complexity, there are two ways. First, using approximate algorithm for preparing quantum state. Next, restricting input space to a special family of quantum state. First, we have two main limitations. First, we prepare a quantum state with inaccuracy, and this accuracy should be up to a level of a specific threshold. In the other hand, developing robust method for fault-tolerant quantum computing with strong error correction is still an obstacle in quantum computing, and preparing quantum state approximately will add more overhead. So we follow the second way, and as a special family of quantum state, we consider uniform quantum state. In uniform quantum state, there is a condition: all amplitude are either 0 or have same value, and that are formulated by 1 over square root of S multiplied to the summation of basis state when amplitude of them is non-zero. And S here represents the number of non-zero amplitude. By this assumption, we can map uniform quantum state to Boolean functions. For example, we have this uniform quantum state, amplitude are either 0 or 1 over a square root of 3, and number of non-zero amplitude is 3. Then we can map this uniform quantum state to this Boolean function. When amplitude is non-zero, the value of Boolean function is 1, and when the amplitude is 0, the value of Boolean function is 0. We also can define a uniform quantum state using min-term of Boolean function. So we have, for this uniform quantum state, we have 3 min-terms. Uniform quantum states are important because they are using in most known quantum states, such as GZ state, Bell state, and W state. They also are using in quantum machine learning as quantum version of uniform random sample. Uniform quantum state also are using in important quantum algorithms such as Grover-Walk, quantum Byzantine agreement, and secret sharing. So uniform quantum state are important, and proposing a special algorithm only for preparation of this important family of quantum state efficiently is important. In this slide, we can see our general method using a Boolean approach. We use the functional decomposition and positive and negative cofactor to prepare quantum states. We do preparation in some order. For example, here we start preparation from Q n minus 1. First, we need to apply a G-gate that results the probability of being 0 for this qubit. Then our quantum circuit divides into two parts. If this qubit is 1, we do same procedure for 0 cofactor by applying negative control to the rest of quantum circuit. If the qubit is 1, we repeat same procedure for positive cofactor by applying a positive control. And we repeat the same procedure for all qubits to create multiple control gate. And finally, we can transform this sequence of multiple control gate to elementary quantum gate using other decomposition method. As a representation of Boolean function, we use decision diagram. In this slide, I want to explain our algorithm utilizing decision diagram using a majority of 3 examples that you can see. It's a binary decision diagram in this figure. For computing 0 probabilities, we need to traverse BDD. First, we traverse BDD from bottom to up to compute the number of 1 for each node that are shown with red color. In next step, we traverse BDD from top to down to compute 0 probability by dividing the number of 1 from 0 child to the number of 1 for current node that are shown with blue color. In last step, we need to traverse BDD from bottom to top to extract multiple control gate. First, for D node, we need to apply a G gate for 0 probability, and then we don't have any child for this node, so we don't need to do anything. And then for C node, we need to apply a G gate with 0 probability on X1 variable or qubit Q1. Then for 0 child or left child, Boolean function goes to 0, so we don't need to do anything. But for right child, we need to apply a positive control to the gate come from D node. Next, for B node, we need to apply a G gate with 1/3 probability. Then for left child, we apply a negative control to the gate from D node, and for 1 or right child, we apply a positive control to the a gate with half probability, because this edge goes to constant 1, and 1 node here is reduced. So we need to apply a half probability gate here. Next, for a node, we repeat same procedure, and so finally in root we can create all multiple control gate. Using a decision diagram causes some advantages. We have a compact representation. We can scale quantum state preparation for a large number of qubits, while state of the art is not applicable. And in some cases, by reducing node embedded, we can also reduce the number of multiple control and elementary quantum gates. We also utilized functional dependencies. In general, we prepare qubit sequentially. Each qubit prepares from all previously prepared qubits, but if we can explore dependencies between qubits, we can prepare qubit depending on a subset of previously prepared qubit instead of all previously prepared qubits. So we utilize functional dependencies to reduce the number of CNOT. To do so, we do this procedure. First, we extract min terms. Next, we consider a variable order for preparation. And then we find dependency between qubits using some method. For example, we have GHZ state with these two min terms, 0, 0, 0, 1, 1, 1. We can extract these two dependencies, x1 or the column corresponding to x1 variable is equal to the x2 and x0 is equal to x2 or x1. And in quantum, we can express equality with CNOT gates. So in V4, we prepare this state using these two, using this circuit. Preparation of each qubit is dependent to all previously prepared qubits. But now, using these two dependencies, we can prepare JZ using only two CNOT that shows each qubit is dependent on a subset of previously prepared qubit. So we can reduce the number of control and finally the number of CNOT. We utilize the two dependency analysis method, pattern-based. In pattern-based, we considered some specific pattern equality, not XOR, XNOR, and NAND. In the second column, you can see their corresponding quantum circuit. And in last column, you can see their cost function, that is the number of CNOT for this pattern with any input. We also use the ESOP-based synthesis. We use SAT-based synthesis to drive an ESOP form of dependency function. Actually, we have XOR of and operations. And we can express them using a sequence of multiple control Toffoli gate. Actually, this method covers all patterns from pattern base and also add one more pattern that is the combination of XOR and AND operations. So in this method, we consider dependencies and we compute their cost function. We compare the number of CNOT from these dependencies and number of CNOT from using general method. If the number of CNOT using this dependency function is less than general method, we apply the quantum circuit corresponding to these dependencies instead of general method. We also found that variable reordering affects CNOT reduction. For example, for this quantum state with these mean terms, we have a dependency and that is x2 is equal to the AND operation of x3 and x0. If we prepare this state with this order, Q3, Q2, Q1, Q0, we can do any optimization and we need to prepare each qubit depending on previously prepared qubit. But if we prepare this qubit with this order, first Q3, Q1, Q0, and last Q2, we can use AND dependency and we prepare Q2 depending on only Q3 and Q0, so we can reduce the number of control and the number of CNOT to 10. In this slide, you can see our result comparison over QisKit. We use the EPFL and ISCOS benchmark. We use cut enumeration to extract Boolean function with different number of qubits. We use the different method of variable reordering, exhaustive reordering that we consider all order and we keep the best one, random reordering that we generate some random orders. We do exhaustive reordering for a small number of qubits up to 5 and random reordering for more. As you can see in last part of table, we can improve and we can reduce the number of CNOT by increasing number of qubits. The result of QisKit is better than us for 4 qubit because they use template and post-optimization method for up to 4 qubits. And also we reduced the other elementary quantum gate, single qubit or rotation gate up to 36%. And also we could reach to speed up to 2 times. In this slide, you can see our result for most for well-known quantum state. We also could reduce the number of CNOT for them up to 56%, and we again could reach speeding up to 2 times over QisKit result. In this slide, you can see my conclusion. We considered a special family of quantum states that are uniform quantum state. We could map them to Boolean functions, so we could use some method from Boolean function to optimize quantum state preparation. We use decision diagram to benefit compact representation and faster simulation, and we utilize functional dependency to reduce the number of CNOT. And both technique and the whole implementation is implemented in our tool Angel that is available in my GitHub. Thanks for your attention.